Hello student. Today I am going to discuss with you this theorem, which is an important theorem on uniformly continuous function. So what does it state? It states that if a function is continuous in closed interval AB, then it is uniformly continuous in closed interval AB. However, the converse need not be true. You can give an example that I have discussed today. That first one, if fx is equal to 1 by x is continuous in open interval 0, 1, but that function is not uniformly continuous. So you can give that example. The converse of this theorem need not be true. So here, if a function, once a function is continuous, this is not true if it is an open interval, I mean. So if a function is continuous in open interval, then it need not be this f need not be uniformly continuous on that interval. You can consider this example 1 by x in open interval 0, 1 that I have discussed today. So here what we have is, suppose here, how to prove it? Suppose f is not uniformly continuous. With f being continuous function, what we need to prove is f is uniformly. Now suppose f is not uniformly continuous in closed interval AB. So if it is not uniformly continuous, it means that there exists an epsilon, a positive real number epsilon greater than 0, such that for all delta greater than 0, there exists 2 points, say x and y, in closed interval AB, such that mod of x minus y is less than delta, but mod f of x minus f of y is greater than equal to epsilon. Because by definition of uniformly continuous, if for every epsilon greater than 0, there exists a delta which depends on epsilon, such that mod f of x minus f of y is less than epsilon whenever mod x minus y is less than delta. But since f is not uniformly continuous, it means that there exists at least 2 points here. There exists point in closed interval AB such that mod x minus y is less than delta, but mod f, the image of this point, f of x minus f of y, is greater than equal to epsilon. So you name it as equation 1. Now, how to get a convergent subsequence, how to get a subsequence from this closed interval AB, we take here, if delta is equal to 1, then there exists, because for all delta greater than 0, so if we take delta equal to 1, then there exists points x1, y1 of closed interval AB such that mod x1 minus y1 is less than 1, but mod fx1 minus fy1 is greater than or equal to epsilon. If delta is equal to 2, again you can find points x2, y2, say, belong to closed interval AB such that mod x2 minus y2 is less than half, but mod f of x2 minus f of y2 is greater than equal to epsilon. Similarly, if you take delta is equal to 1 by 3, then there exists x3, y3 belong to closed interval AB such that mod x3 minus y3 is less than 1 by 3, but mod f of x3 minus f of y3 is greater than equal to epsilon. Continue this process. We obtain two sequences. Two sequences here, this one x1, x2 dash dash xn in particular, and sequence yn in closed interval AB such that mod xn minus yn is less than 1 by n, but mod fxn minus fyn is greater than equal to epsilon for all n belong to n. We obtain those sequences by taking delta is equal to 1, delta is equal to half, delta is equal by 3 dash dash, delta is equal to 1 by n. So there exists point xn, yn in closed interval AB such that mod xn minus yn is less than this. So thus we obtain two sequences xn, where n here belong to the set of natural number. Now as we know that xn is greater than equal to a but less than equal to b, and yn is greater than equal to a but less than equal to b for all n belong to n, that is, if you replace x1 lies between this, y1 also between this, 2 point a and b, for n is equal to 2, the same thing. So both sequence xn and sequence yn are bounded sequence of closed interval AB. Why they are bounded sequence? Because they lies between these 2 points a and b. And by Bolzano-Weierstrass theorem on sequence, every bounded sequence in R has a convergent subsequence. So if it has a convergent subsequence, so this shows that this sequence, since it is a bounded sequence, so by Bolzano-Weierstrass theorem, therefore this sequence xn has a convergent subsequence, say x and k, such that limit of x and k tends to is equal to j, because every by Boltzmann every convergent sequence has a convergence has every bounded sequence has a limit point. I mean, not a convergent, has a limit point. So by Boltzmann-Weierstrass theorem, there exists a convergence. So there exists a convergent sequence x and k of this, a subsequence of this xn, such that subsequence will converge to j as k tends to infinity. And since we know that a closed interval is a closed set, because it contains all its limit point, or we can say that the complement of this set is an open set. So if it is a closed set, it must contain all its limit points. So therefore this j here must belong to closed interval AB. Similarly, for the sequence yn, there exists a convergent subsequence y and k, such that limit k tends to infinity, y and k is equal to n. Now what is equation 1? Equation 1 is this, that there exists point, why it is uniformly not uniformly continuous is that there exists 2 point a xy belong to closed interval AB, such that mod x minus y is less than delta, but mod f of x minus f of y is greater than equal to epsilon. So in particular, you replace this x by x and k and y by y and k. So from 1 we have mod fx and k minus f and yk. You replace that x by x and k in equation 1 and y by y and k, such that we have mod fx and k minus f of y and k is greater than equal to epsilon whenever mod x and k minus y and k is less than 1 by nk, and this is same as less than or equal to 1 by k. Name it as equation 2. Now you can see that this second inequality, not this first one, the second inequality will tend to 0, because as k tends to infinity, 1 by k tends to 0. So this will, as if you take limit x and k minus y and k, will it be equal to 0. That is, the second inequality shows that limit k tends to infinity, x and k is equal to limit k tends to infinity, y and k must be equal, because 1 by k tends to 0. So this shows that what is the limit of x and k as k tends to infinity? By Boltzmann-Weierstrass theorem, this limit converge to j, has a limit point, say j, this subsequence, and again limit y and subsequence y and k converge to eta. So therefore this shows that j and eta, they are the same. And moreover, what is the statement of the theorem? F here is continuous in closed interval AB, and j here being a point of closed interval AB, and j being a point of closed interval AB, what does it mean? That f is also continuous at this point j. So if it is continuous at the point j, and by definition of continuity, if a function f is continuous at a point c, say, then limit x tends to c, f of x must be equal to f of c. So in particular, x here is x and k, and they converge to j. So f is continuous at j. It implies that limit k tends to infinity, using the definition of continuity, limit k tends to infinity, fx and k will be equal to f of j, and limit y and k also, as k tends to infinity, will be equal to f of j. So both they are equal to f of j, since f being continuous and j, and both the subsequents converge to j, as we have seen. Now this implies that limit fx and k tends to infinity, minus this one will be equal to f of j, because both are equal to f of j. So f of j minus f of j, which is equal to 0. So this implies that if this is equal to 0, implies that mod of fx and k minus f of y and k will be less than epsilon. So will be less than epsilon. But what is the first inequality? First inequality from the equation 2. This is equation 2, this whole thing. First inequality from equation 2 we have is that mod fx and k minus fy and k is greater than or equal to 0 epsilon, whereas here we have it is less than epsilon. So which is a contradiction. And why this contradiction arrives? Because we have assumed here f is not uniformly continuous. So hence, if f is a continuous function in closed interval AB, it must be also uniformly continuous in closed interval AB. I hope it is clear to you.